Welcome, VEST scholars, and welcome to this module. In this presentation, we're going to explore the Earth in the context of the solar system. It's just going to be a really broad brush overview, really focusing in on some of the key points that the SOLs here in Virginia try to make with this topic. But throughout this module, we're going to be looking at the Earth's place in the solar system overall. So I'm going to start off with this nice iconic Earthrise photo taken by the Apollo astronauts all those years ago. As we think about returning back to the moon again and then on to Mars, such images will hopefully become the norm in the future. But understanding where we are, I suppose if you're looking at the Earth from the moon, gives you a completely different perspective of our planet and how fragile and how special at the same time that it really is. So to understand it better, let's think about its context a little bit. So first of all, it's important to note that NASA has a lot of hardware in space looking at various aspects of the solar system. These include a wide variety of space telescopes, some of which, like the Hubble, are quite popular and people know a lot about. The Kepler Space Telescope, which is really focused on exoplanets, named after the famous scientist Kepler. And of course, Spitzer and Herschel and WISE, and these, of course, are looking in the different bands of light. So if you're going to detect or create a light detector, you have to design it to detect the particular kind of light you want to study. And certain things in space are best studied in certain wavelengths of light. So our eyes are visible light detectors, but if you want to look at objects in space that emit X-rays, then you have to design an X-ray detector to do that. And you have to put it into the atmosphere or up into space at a certain elevation, or maybe it can be on the surface of the Earth like an optical telescope, where you can make those observations. And so NASA and many, many partner institutions, of course, have been doing this for a very long time. So there's a lot of equipment that's been brought to bear. And this fleet, or this array of material, along with all of the ground-based stuff owned by universities and the other consortia, National Science Foundation, have provided us with the really wonderful insights we have about the space around us. And, we all wonder about it, the science fiction and everything else, but all of that is grounded in fact. And the more we learn about it, the more exciting it all really is. Start, of course, off with the Big Bang, which initially was thought to be a crazy idea because the universe was thought to be steady state and existing forever from a scientific perspective. And of course, it wasn't all that long ago. I don't even think it was a full century ago that the idea of the Big Bang was proposed. And of course, there's important evidence for it. The cosmic microwave background radiation, about 2.7 degrees Kelvin today, was a whole lot more at the Big Bang, and we could trace that back. We can look at the expansion of the universe, in general, the fabric of space-time and its expansion, among many other pieces of evidence. And of course, we come to the conclusion that the universe had a beginning. Now, of course, people talk about multiverses and all that kind of stuff. Well, all we can really talk about is the one we definitely have evidence for, which is our own universe. And so we know it had a beginning. Right now, we don't know that it actually has any kind of an end. So we can't say anything about that, but we can say there was a beginning out of a singularity. Our universe was born, a single high energy state, and eventually expanded into what we have today. And along with that expansion, formed galaxies and matter was able to combine into various patterns, some of which are galaxies. Galaxies, of course, contain stars or star systems, and stars contain around them planets, and that's really what we're going to get at. So, Edwin Hubble, this tuning fork diagram is based on his classification of galaxies, largely Messier objects and so forth. But these galaxies were classified based on their shapes. And galaxies themselves, some of which have existed. Our own Milky Way has probably existed for for definitely more than 5 billion years. That's how old how old our sun is. Perhaps twice that age. It's hard to date things at that scale, but regardless, we can classify galaxies based on this. They come in a variety of shapes and sizes. There are also other kinds of galaxies out there. In this case, these are active galaxies. These are typically objects that have a neutron star or a black hole in this. But these are not galaxies in the sense that they are similar to star systems or galaxies like the Milky Way. A galaxy like this is formed around a supermassive black hole of some kind as well, but just very different in structure. So there are other things that are also referred to as galaxies, but are different and different than what we currently think of and what we live in today. But still very interesting objects and have a lot to teach us about the universe as a whole. Within galaxies are stars, and of course, stars form as clouds or pockets of gas begin to coalesce and begin to rotate, and eventually become hot enough in the center where nuclear fusion can ignite and create a protostar. Depending on the amount of mass in that initial cloud of gas or nebula, the star will be born along some portion of what we call the main sequence, which is all classified based on star color or temperature and its brightness. So the more massive the star, the further up the sequence it'll be born. And of course, the mass of the star will determine its eventual fate. Just like and I will come back to ours in a little bit, but our sun is right here on the main sequence. That's where it was born. So our sun will eventually become a giant star and then eventually peter out to become a white dwarf. And that'll have a very profound effect on our solar system at the time. I mean, it's not going to happen within your lifetime or your descendants' lifetimes or anybody who'll probably remember you lifetime. That's not supposed to be depressing. That's just reality. It's going to be a long time from now. At least probably 4 billion years before you have to worry about it. So it's nothing to be concerned about at the moment. But stars maintain their size through a process called hydrostatic equilibrium, where gravity wants to crush them, but the temperature or the reactions of fusion on the inside want to push them out. And it's ultimately, if we ever are able to produce fusion on Earth, we'll have to find some way to contain the fusion. And in space, gravity does that for stars really, really well. And of course, the bigger the star, the more matter and more mass it has, the more matter it has, the more fusion it's going on, and the bigger it's going to be, and the more gravity has to rein it in. So there's a lot of these factors are the same, whether it's a little star down here like Wolf 359, or up here with Beta Centauri. Okay, so either case, the function is largely the same. Now, when you move over to the giant realm or the supergiant realm, you're moving through, instead of hydrogen fusion, you're moving into helium fusion and then eventually carbon fusion and so forth. Of course, around a star, a solar system can form. And the primary model we use to understand solar system formation is called solar nebula theory. And solar nebula theory posits that at the center of the solar nebula, solar cloud of gas, there's a protostar that provides the energy and the rotation and everything else that's going along with it. And eventually the matter, as the star forms, the matter begins to coalesce and clump together and to form objects we refer to as protoplanets and eventually planets. Till we get to, from a state here, the initial beginning of a solar system, to what we see today in our own solar system. So there's a process here, and this process takes a fairly decent amount of time. So our current solar system is very different than it was 4 billion years ago. So the moon, oops, that took a lot of load. Our moon, for instance, formed right after the Earth did. And as a part of this first part of the early solar system, you have a lot of stuff flying around, bits and pieces of, you can imagine if you've seen Star Wars, the early Star Wars movies, and they come out of warp speed or they come out of hyperspace, as they call it, and they're right in the middle of an asteroid field. And you're dodging asteroids. Imagine that's kind of what you can imagine the solar nebula might have been like. And the early Earth was probably had a molten surface at the time during what we call the Hadean Eon. And because of that, there's objects flying around. We think a Mars-sized object, we give it the name Theia, hit the Earth, probably at a blind side. Here's a computer model simulation of that, playing over and over again. Maybe hit the Earth at a sort of sideswiped it. And of course, parts of the Earth came back and coalesced to form the moon that we have. Our moon or our natural satellite, I should be specific. It's not a moon, it's a natural satellite. To get the terminology correct, our natural satellite is bigger than it probably should be for our planet, and it is in fact, of course, has an outsized tidal effect on our oceans, which is critical. Life has evolved with that, and of course, it's moving away slowly, which also has effects on things. over time. But nevertheless, our natural satellite, the moon, is critical for life on Earth and the Earth system itself and how it behaves. So it's really good that this event happened 4 billion years ago. Although if it hadn't, perhaps things would have evolved without the moon. But okay, so another major event, of course, created the craters on the moon. When you think about the craters, the mare or the seas, or the quote unquote man on the moon, if you will. These are large flows of basalt on the surface of the moon, which is why they're so dark, because basalt is black or dark in color. And it's thought one solution for this is that these were formed during a period called the Late Heavy Bombardment, or the LHB, which occurred between 3.9 and 3.82 billion years ago. About an 80 million year period. Very rapid, very brief. This is just one hypothesis, of course, for the formation of these. And so, of course, one model for that, for the precipitation of the late heavy bombardment, is the Nice model, which is a model that posits that we're going to go back in time here. So I'm going to go ahead and speed it up. That currently we're in a state of stability, but in the early solar system, the outer planets were in a state of instability, in the sense that it has to deal with issues of orbital resonance, one planet versus another. But there was a moment in the solar system's past where that instability was rectified, and when that happened, Saturn and Jupiter moved further out from the sun than they are, and relatively suddenly, it probably took some millions of years, but relatively suddenly, thrusting asteroids in and out of the asteroid belt, or whatever was there at the time, causing big objects to come and hit Mars, come and hit Moon and Earth, and so forth. This is one hypothesis. It's an interesting one, developed in the southern French city of Nice, probably at a cafe. I don't know. It was I'm sure it was a lovely afternoon when they first discussed it and gave it the name Nice model. Regardless, this is an explanation for the late heavy bombardment and the craters that we see on our natural satellite. So moving on here, Keplers, it was always a mystery as to how planets moved around the sun. Of course, it was first we didn't think planets actually moved around the sun. We thought that the planets and the sun moved around the Earth. That was the geocentric universe that Galileo and Copernicus gave to us. But their version of it had perfectly circular orbits, so it retained that Aristotelian perfection on some level. It wasn't until Johannes Kepler, a mathematician later on in the 1600s, was able to take observations he and Tycho Brahe had made and turn them into calculations that produced the three laws that Kepler that are named after him. And you'll deal with these in this module. So Kepler's first law is very simple. All planetary orbits are elliptical. There's no such thing as a circular orbit in the universe, or at least in our solar system. Now, you can have pretty darn close to circular, but you don't have circular orbits. The second law is a little weird to think about. If you take a line and you have it sweep over an area along one portion of an orbit, a line from the sun to the planet, and then do the same thing in another area, a line swept over that will have the same distance if the areas are equal. So these areas, area X and area Y, are equal areas, but you'll note that over here, the distance covered by the planet is much greater than it is over here. The net effect of this is that because the orbits are elliptical, the sun is going to be located at one of the foci of the ellipse, because while a circle has one focus from which you measure the radius, an ellipse has two foci, and the sun is going to be located at one of those foci. And as the planet approaches the sun, it speeds up. Its velocity is faster, and then it slows down as it gets further away again. And you can kind of see that a little bit happening over here as this one moves around, and you see the equal areas. And it moves around the sun really fast like that. The third law is related to the distance from the sun that the planet is, and then the time it takes to get around the orbit. So it's actually a corollary of the second law, and that there's an actual relationship between distance and how fast the planet gets around the sun. And i.e., what ends up happening being the case here is the net effect is the distance dictates how long a year is. So a year, of course, on Earth is defined as by 365.25 days, which is the time it takes the Earth to get around the sun. Likewise, every other planet a year is defined the same way, or at least we define it that way. And of course, the distance of that planet from the sun determines how long that year is going to be. It doesn't determine how long the day is. The rotation's a whole different animal. But these are Kepler's three laws. The first law, elliptical orbits. Second law, the law of harmonies. And then the third law, the law of, actually, I think this might be called the law of harmonies. It doesn't really matter what it's called. The second and third law, for the most part, getting them mixed up here for you, are important for determining how a planet moves around the sun. So, of course, we have the inner planets. You're familiar with Mercury, Venus, Earth, and Mars. And between the inner planets and the outer planets, the inner planets, of course, are our terrestrial planets, is the asteroid belt. Asteroids are moving around about 18 kilometers per second. It's a happening place, although if you were to fly through it, you might not see an asteroid. It's not a very populated place. But it is nevertheless a place where we do sometimes get incursions from. So the asteroid that killed the dinosaurs, I can't say for sure that it came out of the asteroid belt, but that's one possible location. The moon, the natural satellites that Mars has, Phobos and Deimos, are very likely captured asteroids, although that's not absolutely confirmed either. And then you have the outer planets here, Jupiter, Saturn, Uranus, and Neptune. And of course, these are gas giants, or in the case of these two, ice giants. So they're much, much colder. As we get further out into the solar system, the temperatures are much colder. And then we have, of course, another classification of planets brought to us by the International Astronomical Union in 2006 when they came up with a definition of a planet. And these are the dwarf planets. These are a few of them. And of course, Pluto, which when I was a kid was a planet, now is a dwarf planet. There's some move to try to, reassess this definition, but that's not really getting anywhere at the moment. All right, so moving on here, there's other important parts of the solar system, including, of course, comets. And of course, comets are distinctive from asteroids because they're generally frozen. And the comets are coming from further out in the solar system. Two places we refer to. One is the Kuiper Belt, and one is the Oort cloud. Still not very well studied. In fact, the New Horizons mission is out there studying Kuiper Belt objects right now after it left Pluto. So we're still getting really great insights into that. The Oort cloud is a whole other thing. The Oort cloud, as it's conceived of, is surrounds the entire solar system, not just in the plane of the solar system. So we think of long period comets as coming from there. These are comets whose orbits are well over 1,000 years or more, and then of course short period comets coming from the outer part of the solar system, the Kuiper Belt. All right, now planets, of course, to be habitable, have to be within the habitable zone of a star, and the habitable zone, as we define it, generally means that liquid water can exist on the planet because life as we know it requires liquid water. And so, of course, that means that certainly limits the number of planets out there that can be considered for life. And so generally in our solar system, the Earth is right in the Goldilocks zone, if you will. If you think back to the Goldilocks and the Three Bears and all those things in the house that were just right, that's exactly where that comes from. So as we think about exoplanets and that are out there and the possibility for them to harbor life, it's important that we look for stars with the right characteristics, and we look for planets that locate at the right distances from those stars. And okay, so eventually, of course, the Earth is going to have a fate of its own. The universe may keep on going, but the Earth will have an end. And of course, the Earth's end is going to be entirely dependent upon the fate of the sun, and the sun's life will come to an end as well. Again, the universe will keep on going, but the sun will come to an end. And so when that happens, the sun will begin fusing helium in its core. It will swell to the size of a red giant, which may end up actually encompassing the Earth inside of the sun, at which point it no longer exists. Or at best, Earth becomes more like a Mercury-type planet where the atmosphere is baked away and there's nothing left but rock. But that won't happen for a very long time, so don't worry about it. All right. Well, I hope you've enjoyed this overview of the Earth and its place in the solar system. Remember to check with your master teachers for questions, and thanks for listening.